Imagine for a moment that you are looking at a wall, a simple, solid wall. It appears permanent, impenetrable, utterly dependable. You could lean against it, you could paint it. You could spend your entire life confident that this wall will never, not once, spontaneously appear on the other side of your house. But here is the truth that will unsettle everything you think you know about reality. That wall, at this very moment, has a small but mathematically real probability of doing exactly that. Of vanishing from here and materializing over there. The wall doesn't do this, of course. Not in any time frame that matters to creatures like us. But the fact that it could, that the mathematics of the universe permits it, reveals something so strange about the nature of existence that once you see it, you cannot unsee it. The rule that governs this madness is breathtakingly simple. You cannot know everything, not because you lack the tools or the intelligence, but because the universe itself does not permit it. Reality at its deepest level is irreducibly probabilistic. It is not that we don't know where an electron is. It is that the electron does not have a definite position until the moment you look. This is quantum mechanics. And from this single, utterly alien principle, you can reconstruct the entire architecture of atoms, the stability of matter, the source of sunlight, and the reason you exist at all. Let's start with the impossibility. In the world you see around you, things have properties. A ball is here or there. A car is moving at this speed or that speed. You can, in principle, know everything about an object if you measure carefully enough. This seems obvious. It seems like the basic contract of reality. But it is wrong. Completely, fundamentally wrong. In 1927, Werner Heisenberg discovered something that shattered this contract. He found that certain pairs of properties are locked in an eternal trade-off. The more precisely you know one, the less precisely you can know the other, not because your instruments are crude, but because the universe forbids the knowledge. The most famous pair is position and momentum. If you know exactly where a particle is, you know nothing about how fast it's moving. If you know exactly how fast it's moving, you cannot say where it is. This is not a measurement problem. This is reality itself, refusing to be pinned down. Think about what this means. It means that an electron does not have a trajectory in the way a baseball does. A baseball at any moment is at a specific location moving with a specific velocity. You could, if you were clever enough, predict exactly where it will be at any future time. But an electron is smeared across space, a cloud of probability, until you look at it, and the instant you look, the cloud collapses, the electron appears in one place, and the universe makes a choice it had not made before. This is not philosophy. This is measurement. This is what happens. Now here is the first great secret. Nobody knows why. We can calculate the probabilities with stunning precision. We can predict the outcome of experiments to 15 decimal places, but the why, the mechanism behind the collapse, the reason reality works this way, remains one of the most profound mysteries in all of science. It is simply a rule of existence, an axiom of our reality. And it is nothing like the world you see when you open your eyes. Back to the electron. If you cannot know both where it is and where it's going, what does it mean to say the electron is somewhere? The answer that emerges from the mathematics is strange beyond belief. The electron is, in a very real sense, everywhere it could be, all at once. It exists in what we call a superposition, a simultaneous blending of all possible states, each weighted by a probability. Only when you measure does the superposition collapse into a single outcome. Before measurement, the electron is not hidden in one location, waiting to be found. It genuinely inhabits all allowed locations simultaneously. This leads to the famous double-slit experiment, perhaps the most beautiful and disturbing demonstration in all of physics. Fire electrons one at a time toward a barrier with two slits. On the far side, place a detector screen. What happens? Common sense says each electron goes through one slit or the other and hits the screen, building up two bright bands opposite the slits, but that is not what happens. Instead, you get an interference pattern, alternating light and dark bands, exactly like the pattern you see when waves of water or light pass through to slits and overlap. The electron, a single particle, interferes with itself. It acts as though it went through both slits simultaneously, like a wave spreading through both openings and recombining on the other side. How can a single, indivisible particle do this? The only coherent answer is that it did go through both slits. Before measurement, the electron exists in a superposition of going through the left slit and going through the right slit. Both possibilities are real, both are happening, and they interfere with each other. Now comes the truly eerie part. Place a detector at the slits to see which one the electron goes through. The moment you do, the interference pattern vanishes. You get two bands, exactly as common sense predicted. The act of measurement, the act of asking the universe to commit to an answer, destroys the superposition. The electron, forced to choose, goes through one slit or the other, and the wave-like interference disappears. Reality itself changes depending on whether you look, not because you disturb it mechanically, though that happens too, but because the act of observation is woven into the fabric of what is real. This is not a trick. This is not a misunderstanding. This is nature telling us that the universe at its foundation is not made of little billiard balls following predetermined paths. It is made of something far stranger. Something that defies every intuition evolution built into your brain. Richard Feynman himself said it best. If you think you understand quantum mechanics, you don't understand quantum mechanics. Nobody does. We can calculate it. We can use it. But understanding, in the everyday sense of the word, is denied to us. Now hold two thoughts in your head. First, this is not confined to the atomic scale. In principle, quantum mechanics applies to everything. The wall, the chair, you, every object is described by a wave function, a mathematical expression that encodes all possible states the object could be in. For large objects, the probabilities become so overwhelmingly concentrated around a single outcome that the quantum effects vanish into irrelevance. The wall does not noticeably tunnel across the room because the probability is so fantastically small that it would take longer than the age of the universe raised to the power of the age of the universe for it to happen once. But the mathematics says it is not zero. The wall is technically in a superposition of being here and being over there. Reality at the macroscopic scale is the limit where quantum strangeness averages out to. Classical predictability. Second, this strangeness is not a bug. It is the foundation of stability. Consider the atom. An electron orbits a nucleus bound by electrical attraction. But classical physics has a fatal problem. An accelerating charged particle radiates energy. An orbiting electron is constantly accelerating, constantly turning. It should radiate its energy away and spiral into the nucleus in a fraction of a second. Every atom should collapse instantly. The universe should not exist. Quantum mechanics solves this. The electron does not orbit like a planet. It occupies an orbital, a three-dimensional standing wave of probability surrounding the nucleus. And these orbitals come in discrete sizes, specific allowed patterns, like the harmonics on a guitar string. The electron cannot spiral inward continuously because there is no orbital between the lowest energy level and the nucleus. It is stuck. There is nowhere lower to go. The electron is confined to specific quantized states, and this quantization, this discreteness forced by the wave nature of matter, is what keeps atoms from collapsing. The solidity of your hand, the stability of matter itself, rests entirely on quantum mechanics. This quantization has another stunning consequence. Atoms can only absorb or emit energy in specific amounts corresponding to jumps between allowed orbitals. When an electron drops from a higher orbital to a lower one, it releases the excess energy as a photon of light. The color of that light, its frequency, is determined by the energy difference between the levels each element has. A unique set of orbitals, and therefore a unique set of allowed jumps, and therefore a unique spectrum of light. The yellow glow of sodium streetlights, the red of a neon sign, the dark lines in the sun's spectrum, all are fingerprints of quantum jumps in atoms. Spectroscopy, the science of reading these fingerprints, lets us determine the composition of distant stars without ever touching them. We know what the sun is made of because quantum mechanics dictates what light it can emit. Now the plot thickens beautifully. Quantum mechanics has a secret twin, quantum field theory. They seem related but distinct. One describes particles, the other describes fields. But they are two faces of a single coin. In quantum field theory, what we call a particle is actually a localized excitation in a field that permeates all of space. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. Fields are fundamental, particles are what fields do. And here is where it becomes sublime. The vacuum, empty space itself, is not empty. It seethes with quantum fluctuations, brief spontaneous appearances of particle-antiparticle pairs that flash into existence and annihilate in timeframes so short that Heisenberg's uncertainty principle permits it. Energy can be borrowed from nothing, as long as it's paid back quickly enough. The vacuum is a boiling froth of virtual particles, an energetic chaos underlying the apparent calm of empty space. This is not speculation. These virtual particles have measurable effects. They alter the energy levels of atoms in ways we can detect. They create a tiny attractive force between metal plates placed very close together, the Casimir effect, because the space between the plates excludes certain wavelengths of virtual particles, creating an imbalance in the quantum vacuum pressure. The vacuum pushes. We have measured this. The nothing is something, and it has consequences. This union of quantum mechanics and field theory, developed by Feynman and others in the mid-20th century, yielded an even more stunning truth. Feynman invented a new way to calculate what happens when particles interact. Instead of solving equations directly, you draw pictures, now called Feynman diagrams. Each diagram represents a possible way an interaction can occur. An electron emits a photon. The photon is absorbed by another electron. They repel, but quantum mechanics says that every possible path, every possible sequence of events happens simultaneously in superposition. You must sum over all possible diagrams, all possible histories, to get the final probability. This is the path integral formulation. To find the probability that a particle goes from here to there, you consider every possible path it could take. Straight lines, wild loops, detours through Alpha Centauri. Every path contributes to the final answer, each with a different probability amplitude. Most paths cancel out through quantum interference, and what remains is the classical trajectory, the path of least action. But the other paths, the crazy ones, are still there, influencing the outcome at the quantum level. The electron going from A to B does not take one path, it explores all paths, and the universe averages over them. When Feynman calculated the strength of the electron's magnetic field using this method, the prediction agreed with experiment to 11 decimal places. Later refinements pushed it to 15. This is the most precisely verified prediction in the history of science. Quantum electrodynamics, the theory of light and matter, is astonishingly, unreasonably accurate. It works. And yet, ask what it means for an electron to take all paths at once, and you fall into the same interpretive abyss that has swallowed every generation of physicists since 1927. Let this truth settle into your bones. Particles can tunnel through barriers they do not have enough energy to cross. An electron confronted with a wall does not always bounce back. There is a small probability it appears on the other side, having passed through the classically forbidden region without ever being inside it. This is quantum tunneling, and it is not rare. It is how the sun shines. Inside the sun's core, hydrogen nuclei collide. To fuse, they must overcome the electrical repulsion between their positive charges and get close enough for the strong nuclear force to bind them, but the temperature of the sun's core is too low. The nuclei do not collide with enough energy to overcome the repulsion barrier. Classically, fusion should not happen. The sun should be dark. But quantum mechanics permits tunneling. A small fraction of collisions results in the nuclei tunneling through the electrical barrier and fusing on the other side. This is enough. The sun shines because of quantum tunneling. You exist because particles do not always obey the classical rules. Tunneling is also why radioactive decay happens. An alpha particle, a clump of two protons and two neutrons, can be trapped inside a heavy nucleus by the nuclear force. It does not have enough energy to escape. But the walls of this nuclear prison are not absolute. There is a probability, however small, that the alpha particle tunnels out. Eventually, it does. The nucleus decays. This is random. Utterly, fundamentally random. You cannot predict when a particular nucleus will decay. You can only give the probability per unit time. Quantum mechanics is irreducibly statistical. Now imagine deliberately using this randomness, this inability to predict individual events. You get the atomic bomb, where a random tunneling event in one nucleus triggers a cascade. You get nuclear power, you get radiometric dating, reading the age of rocks by counting decay events. You get medical imaging, using radioactive tracers that decay and emit detectable radiation from inside your body. All of this rests on the foundation of quantum uncertainty. This leads to a profound realization. We think of the solid, predictable world as fundamental and the quantum realm as a strange exception. It is not. The quantum realm is fundamental. The classical world is an illusion, a statistical averaging over countless quantum events. Determinism, predictability, the sense that the future is fixed by the present, these are emergent properties, patterns that appear when you zoom out far enough. At the bottom, there is only probability. Now hold two more thoughts. First, quantum mechanics has given us the transistor, the laser, the MRI scanner, the LED, the computer chip. The entire digital age is applied quantum mechanics. Every screen you look at, every message you send, every calculation your phone performs, all of it relies on controlling electrons in quantum states. We have learned to engineer the wave function itself, to trap electrons in potential wells of our own design, to make their quantum properties work for us. Technology is now quantum technology, whether we call it that or not. Second, we still do not know what happens during measurement. The wave function collapses. Superposition becomes a single outcome, but how? When? What counts as a measurement does it require? A conscious observer, or is any interaction enough? This is the measurement problem, and it has spawned a dozen competing interpretations. In the Copenhagen interpretation, the wave function is not real, it is just a tool for calculating probabilities, and collapse is a fundamental process. In the many worlds interpretation, the wave function never collapses. Every possible outcome happens, but in separate, branching universes. When you measure the electron's position, the universe splits. In one branch, you see it here. In another, you see it there. Both are real. We do not know which interpretation is correct. We may never know. The mathematics is the same for all of them. They make identical predictions for every experiment we can perform. The interpretations differ only in what they claim is real, and reality at this level may be forever beyond our reach. Feynman himself refused to commit to an interpretation. He focused on the calculations, the predictions, the things we can test. The rest, he implied, is not physics, it is metaphysics. Even the awesome power of quantum computing is, at its moment of operation, a controlled exploitation of superposition. A classical bit is either 0 or 1. A quantum bit, a qubit, can be both a superposition of 0 and 1 until measured. String together many qubits and you create a system that explores many possibilities simultaneously in parallel across the superposition space. For certain problems, this parallelism offers exponential speedup. A quantum computer does not just calculate faster, it calculates differently, harnessing the strangeness of quantum mechanics to perform tasks that would take classical computers longer than the age of the universe. So, we have learned to describe this strangeness. We can predict it, harness it, and weave it into the fabric of modern civilization. We can say what it does with phenomenal accuracy. But the deepest question remains unanswered. Why does reality work this way? Why is the universe probabilistic? Why does measurement collapse the wave function? We do not know. We have found a pattern, a beautiful, powerful, all-encompassing pattern, and we have given it equations. And that perhaps is the most Feynman insight of all. Physics does not give us ultimate whys. It reveals profound hows. It shows us the patterns in nature's tapestry, even when those patterns defy every instinct we possess. Quantum mechanics is one of the most fundamental of those patterns. It is the pattern of uncertainty and superposition that stabilizes atoms, powers the sun, enables chemistry, and underlies the entire material world. We have learned to read the pattern, to use it, to build technologies that would seem like magic to previous generations, but the reason for its existence remains a glorious mystery. The universe is under no obligation to make sense to us. It is under no obligation to match the world of our intuition, the world of medium-sized objects moving at medium speeds that our brains evolved to navigate. Yet here we are, having deciphered enough of this strange quantum reality to split atoms and light the world. And the mystery itself is not a closing door, but an invitation, a sign that there's always more to discover. Consider this. Right now, as you read these words, the electrons in the atoms of your body are in superposition. They are not in one place. They are spread across a cloud of probabilities, constrained by the laws of quantum mechanics into orbitals that keep you stable and solid. The photons hitting your retina, carrying the information of the letters, are themselves quantum objects, particles and waves simultaneously, their properties undefined until the moment they are absorbed by the molecules in your eye. The solidity you feel, the colors you see, the thoughts forming in your brain as electrochemical signals race along neurons, all of it is quantum mechanics in action. You are not separate from this strangeness, you are made of it, and yet you do not feel it, not a whisper. The quantum world reveals itself only through careful experiment, through double slits and interference patterns and tunneling probabilities. In everyday life, the probabilities collapse so quickly, the superpositions decahere so fast due to interaction with the environment that the quantum vanishes and the classical emerges. You see a world of definite outcomes, of objects with positions and velocities, of causes followed predictably by effects. The quantum supports the classical but remains hidden beneath it like a stage behind the curtain. This is the central tension of quantum mechanics. It works. It explains everything from the structure of atoms to the behavior of semiconductors to the radiation signature of black holes. No experiment has ever contradicted it, and yet it describes a reality so alien to our experience that even those who use it daily struggle to say what it means. Niels Bohr, one of the founding architects, said that anyone who is not shocked by quantum theory has not understood it. Feynman said that nature's imagination is far greater than man's. The universe has constructed itself on principles that mock our intuitions, and we are left to calculate and wonder. What does it mean for something to be in two states at once? What is a wave function, truly? Is it real, a physical field rippling through space, or is it just a mathematical tool, a placeholder for our ignorance? When the universe makes a choice during measurement, does something real happen, or is the choice an illusion, a localized perspective? On a much larger, deterministic reality, these questions have occupied the finest minds for a century, and consensus remains elusive. Some physicists embrace the mystery and move on, focusing on calculations and predictions. Others search for deeper theories, hoping that quantum mechanics is an approximation, a shadow cast by a more fundamental reality that makes sense: string theory, loop quantum. Gravity, pilot wave theory, these are attempts to go deeper, to find the mechanism beneath the pattern. But so far, quantum mechanics stands unshaken, its predictions verified, its mysteries intact. Here is what we know for certain. Quantum mechanics is the most successful theory in the history of science, measured by predictive accuracy. It has never failed a test, every technology that defines. The modern world, from the smartphone in your pocket to the solar panels on rooftops to the medical imaging that saves lives, depends on our understanding of quantum principles. We have bent the quantum world to our will, manipulating individual atoms, trapping ions in electromagnetic fields, entangling photons across kilometers, building machines that operate in the regime where classical intuition fails completely, and we have barely scratched the surface. Quantum entanglement, the phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, regardless of distance, remains deeply mysterious. Einstein called it spooky action at a distance and spent years trying to prove it couldn't be real. He was wrong. Entanglement is real. Experiments have confirmed it beyond doubt, and yet we cannot use it to send information faster than light, cannot violate causality, cannot break the universe. The rules hold even when they seem impossible. Entanglement suggests that the universe is not made of separate, independent pieces. At the quantum level, everything that has interacted remains connected, part of a larger, indivisible whole. Separateness is an illusion, a useful approximation that breaks down when you look closely enough. You are not an isolated collection of atoms. You are a temporary pattern in a quantum field that extends across the cosmos, entangled with everything you have ever touched, every photon you have ever emitted, every breath you have exhaled. The boundaries are fuzzy. The separateness is provisional. This is not mysticism. This is the mathematics, followed to its logical conclusion. And it suggests something profound. The universe is not built from things. It is built from relationships, from correlations, from information encoded in quantum states. Matter is not fundamental. Fields are fundamental. Particles are excitations, and consciousness, the one phenomenon that seems most resistant to physical explanation, may be an emergent property of sufficiently complex quantum information processing. We do not know, but the door is open, so where does this leave us? We stand at the edge of a mystery, armed with equations that work, but explanations that falter. We can calculate the probability that an electron will be here or there, that a photon will be absorbed or reflected, that a nucleus will decay. In the next second or the next millennium, we can build technologies that manipulate quantum states with extraordinary precision. We can peer into the heart of atoms and see the wave functions dancing. But we cannot say why the universe is quantum. We cannot explain why reality refuses to commit until observed, why particles interfere with themselves, why the vacuum seethes with virtual fluctuation. These are the rules, not the reasons, and perhaps there are no reasons, no deeper layer, no final answer. Perhaps the universe simply is, and the patterns we observe are the shape of existence itself, irreducible and unexplainable. Or perhaps we are missing something vast and obvious, a conceptual shift as revolutionary as the one that gave us quantum mechanics in the first place, perhaps. Future generations will look back at our confusion with the same bemusement we feel reading about the ether or caloric fluid, mistakes made by brilliant people who lacked the right framework. Perhaps the measurement problem will be solved, the interpretations unified, and the strangeness will dissolve into a clarity we cannot yet imagine. Or perhaps not, perhaps the mystery is permanent, a feature of reality that no amount of cleverness can eliminate. Perhaps we are asking questions that have no answers, seeking understanding in a domain where understanding is forbidden. The universe, after all, is under no obligation to provide us with satisfying narratives. It simply does what it does, indifferent to our need for comprehension. And yet, we continue. We ask, we experiment, we calculate, we build theories and test them and refine them. We push into the unknown, driven by a curiosity that is itself inexplicable, a quantum fluctuation of consciousness in an indifferent cosmos. And in doing so, we have illuminated the darkness, split the atom, touched the moon, and decoded the quantum signature of reality. The mystery remains. But the mystery itself is not a failure. It is a testament to how far we have come and a promise of how far we might yet go. Quantum mechanics is not the end of physics. It is a beginning, a doorway into a stranger and deeper reality than our ancestors could have imagined. And we are only just learning to read the signs. So, we have learned to describe this pattern. We can predict it, harness it, and weave it into the fabric of civilization. We can say what it does with phenomenal accuracy. But the deepest question remains unanswered. What is a quantum state? Why does measurement collapse superposition? Why is the universe probabilistic at its core? We do not know. We have found a pattern, a beautiful, powerful, all-encompassing pattern, and we have given it equations, diagrams, names. And that perhaps is the most Feynman insight of all. Physics does not give us ultimate whys. It reveals profound hows. It shows us the patterns in nature's tapestry, even when those patterns violate every intuition evolution built into our minds. Quantum mechanics is the deepest of those patterns. It is the pattern of uncertainty and superposition and entanglement that structures atoms, powers stars, enables chemistry, and makes consciousness possible. We have learned to read the pattern, but the reason for its existence remains a glorious mystery. The universe is under no obligation to make sense to us. Yet here we are, having deciphered enough of this silent, quantum strangeness to build computers, cure diseases, and peer into the first moments after the Big Bang, and the mystery itself is not a closing door but an invitation, a sign that there is